during the Myanmar earthquake on 28th of March this year. May I request you for standing, please. Thank you very much. Now, I would like to invite Mr. Asair Sukhyang, President of ASA, to deliver his opening remarks. Please.
Hello, everyone. I'm Asair Sukhyang, President of Association of Architects, Siamese Architect under Royal Patronage. First of all, I will welcome you all to the ASA Expo, which is our annual, biggest annual of the year. There's an Architect Expo upstairs. And will be a welcome speech. Ladies and gentlemen, distinguished guests and dear colleagues, and all international guests, it is my great pleasure to welcome you to the seminar, Enhancing Earthquake Resilience in Bangkok, Review Update and Risk Management. I would also like to extend our sincere appreciation to the International Emergency Management Society teams and their valued support in this meaningful event. Although Bangkok is not widely known as the earthquake risks, recent development remind us of the importance of preparedness. As professionals responsible for the built environmental, we have a duty to ensure safety, resilience, and readiness for unforeseen events. The seminar offers a timely opportunity to share insight and discuss ways to strengthen our city. I thank all the speakers, partners, and participants for your continued contribution and wish the event every success. Thank you. And please have some time to visit us around the expo. Thank you.
Thank you so much, President of ASA. I note that we do not have a representative from the Governor of Bangkok, so we will have Executive Director of NDWC and followed by the team president who will address this meeting. But because of the president will need to leave, I like to maybe ask the representative of NDWC to come to receive a gift of appreciation from the President of ASA. Yes, please. For other speakers, I will send you virtually. Sorry. Thank you so much. I'd like to express my sincere gratitude to ASA for kindly host this meeting in collaboration with team. Without your support, we will not be able to organize this on a timely manner. Thank you so much. Thank you. I wonder whether we should have a group photo from people who come up a moment ago. And I'd like to invite the Deputy President also, the Vice President, for taking photo. Group photo. Next, may I invite the Executive Director of National Disaster Warning Center, Mr. Am Jintanadilok, to deliver his address.
Good morning, everyone. My name is Am Jintanadilok. I am a section director of academic section in National Disaster Warning Center, DDPM. The president of ASA, the president of teams, invite speaker and moderator, distinguished guests, ladies and gentlemen, it is my great honor and pleasure to attend and to deliver my opening address at the workshop entitled Enhancing Earthquake Resilience in Bangkok, Review, Update, and Risk Assessment. This can be served as an important platform that brings together key experts from multi-sector involved in reducing the risk of earthquake in Bangkok. In December 2024, a total of 1,374 earthquakes with magnitude of 5 or more were recorded worldwide from 2000 to 2024. These large earthquakes generally result in high death tolls in developing countries. All countries where building codes are less stringent. China has suffered from a number of strong earthquakes that have resulted in extremely high death tolls. Wide earthquakes occur around the globe along the various tectonic plate boundaries. A significant proportion occur around the basin of the Pacific Ocean, in what is referred to as the Ring of Fire. Due to the high degree of tectonic activity, many of the countries in the Ring of Fire, include Japan, Chile, the United States, and New Zealand, led the way in earthquake policy and science as a result. The tragic loss of life is not the only major negative effect of earthquake. A number of earthquakes have caused billions of dollars worth of damage to infrastructure and private property. The high cost of damage in 2011 Fukushima and Christchurch earthquake in Japan and New Zealand, respectively, demonstrate that even wealthy developed countries who are experienced in dealing with the earthquake are ill-equipped when the large earthquake hit. Thailand, like vast region of the basin and range, has not had a historical large magnitude earthquake and therefore is not generally considered seismically active. The geological record, however, suggests that these generally quiescent faults have been the source of large earthquakes, and if earthquake processes are comparable to those in the Brazil and Range province, earthquake as large as magnitude 1.7 to magnitude 1.3 occur. Though Bangkok is located at a remote distance from seismic source, recent seismic hazard studies show that Bangkok is at risk from damaging ground motion induced by distant large earthquake. This risk is primarily caused by the ability of thick soft superficial deposit in Bangkok to amplify earthquake ground motion about 3 to 5 times. The destructive Andaman-Sumatra fault to the west of the country and the Skyline fault in the east central Burma basin to the northwest of Thailand are a few hundred kilometers from the nearest city of the kingdom. 9 major fault systems have been identified in Thailand. This includes the Thorn Fault, Masariang to Mae Hong Son Fault, and Mui to Uthai Thani Fault. In the northwest of western part of Thailand, Sisawat Fault, Three Pagoda Fault, Ranong Fault, and the Marui Canal Fault. With human life and livelihood at stake, every measure capable of reducing risk and mitigate the impact of natural and human-induced disaster must be used to the fullest. This includes incorporating what is known of potential disaster in the planning of development and infrastructure, and take steps today to lessen the effect of future disaster. On behalf of NDWC DDPM, I would like to express my sincere gratitude to ASA and teams and their partner for organizing this expert consultation workshop on a timely manner. I would also like to extend my sincere appreciation to invite experts both from abroad and from Thailand for their significant contribution. I encourage all of you to use this platform to exchange ideas, share experience, and provide recommendations so that we may enhance Bangkok and Thailand's readiness, resilience, and safety in the face of future potential earthquake. I wish this workshop a great success. Thank you very much.
Thank you very much. And now I'd like to invite Mr. K. Harrell Drescher, the President of International Emergency Management Society teams. Apart from opening address, he will brief of the 2011 conference outcomes and progress made. May I invite Mr. Drescher, please. He will be on Zoom.
I'm addressing you from Norway this morning, and I should have been in Thailand, but unfortunately I...
Excuse me, sir. Please wait a minute until we load your on Zoom. Kindly shown on screen, please. Okay, so Sir, we just have a technical problem that we could not show your on screen at the moment. The technician is coming. Could you please hold on for a minute? Because we'd like to see your face also. Mr. Harodecha is the president of Teams, and he is having online to us from Norway. So it will be our good opportunity to see him and interact with him online. In order to not to have a silence mode, I'd like to move to the to tell you about the next session. After this opening ceremony, we will proceed for the expert session. And we have today 5 invited experts. I think that you have received the final program from me. I'd like to mention about the first speaker. We have Associate Professor Dr. Thirapan Ontamarat from Department of Civil and Environmental Engineer, Faculty of Engineering, Mahidol University. And he will speak on the latest data and models for assessing earthquake risk in Bangkok, considering distant large earthquakes. Then after that, we will proceed for the next speaker on the case study, lesson from recent earthquake. We're ready. Okay, now may I invite Mr. K. Harodecha to give an opening address.
Thank you, Shadrach. President of ASA, representative of Executive Director of NDBC, Ambassador of Bangladesh and Diplomatic Mission in Thailand, international organization, distinguished speakers and participants, ladies and gentlemen. It is indeed my great honor and pleasure to address the international workshop on enhancing earthquake resilience in Bangkok. On behalf of the International Emergency Management Society, TEAMS, I would like to acknowledge with gratitude the Association of Siamese Architects under Royal Patronage, ASA, and the relevant partners for co-organizing the workshop on a timely manner in Bangkok. Let me begin by elaborating about my organization, TEAMS, and the work we do. TEAMS is a global forum for education, certification, and policy in emergency and disaster management. TEAMS is dedicated to developing and bringing the benefits of modern emergency management tools, techniques, and good industry practice to society for a safer world. This is accomplished through the exchange of information, methodology, innovations, and new technologies to improve society's ability to avoid, mitigate, respond to, and recover from natural and man-made disasters. TEAMS provides a platform for all stakeholders within the global emergency and disaster management community to meet, network, and to learn about new technical and operational methodologies. TEAMS also aims to exchange experience on good industry practices. We expect this will influence policymakers worldwide to improve global cooperation and to establish global standards within emergency and disaster management. TEAMS has an international network of more than 80,000 experts worldwide, and such a network can be very valuable for finding expertise and for the exchange of experience and knowledge. Then first, I would like to recap of the 2011 stakeholder consultation workshop outcomes and the progress made since then. The organization of this workshop, entitled Stakeholder Consultation Workshop on the Effects of Distant Large Earthquakes on Infrastructure in Bangkok, Legal, Engineering and Risk Reduction Perspectives. This was a good initiative made by the International Ocean Institute in collaboration with National Disaster Warning Center. Stakeholders, namely the Bangkok Metropolitan Administration, government departments, private sector, and business entrepreneurs, academic institutions, and non-government organizations, including my organization's teams. We were able to share lessons learned with both local and international experts to develop practical Thailand earthquake risk reduction measures. The workshop presented the current state of seismic risk in Bangkok from distant large earthquakes, earthquake risk reduction solutions with experiences from Japan, Mexico, USA, and Turkey, risk management decision support system and concept of operation, cognitive capacity and mitigation preparedness, public and public agency response, involvement of private sectors and business entrepreneurs to advocate people in Bangkok. The basic issues that were addressed at the Bangkok workshop were the probability of and the magnitude of a distant large earthquake and its effect on Bangkok infrastructure, and then addressing how to reduce consequences by building code implementation in Bangkok. However, additional items of importance which were considered and discussed were damage assessment, insurance companies' role and involvement, public awareness, media's involvement and coverage, education about the risks, hazards and consequences, and also other hazards of Bangkok. It was important with a holistic approach in order to arrive at a useful and productive outcome of the Bangkok workshop in 2011. So that was what happened in 2011. But what have been done in Bangkok and Thailand with the suggestions we did in 2011? I have a list here which I will go through. The Bank of Ayurveda public company has considered a pilot case study on retrofit and possible actions on its headquarters building. This was made successfully by providing a retrofitting plan, but not physically. The Association of National Disaster Prevention Industry and the BNA should meet to discuss a plan on retrofit issues. They considered priority actions on schools and hospitals in Bangkok. This has not been made as planned. The public relations team will continue to promote public awareness in all possible ways, including interactive website, media awareness, and face-to-face public awareness. This has not been made as planned. The IOI and Institute of Earth Sciences proceeded for the follow-up of the questionnaire survey to assess Thailand's national capacity on the effects of distant large earthquakes on infrastructure in Bangkok and major cities in Thailand. A strategic planning workshop was organized on May 15, 2012, to present the outcome from the questionnaire analysis and to plan for strategic action. This was made successfully. The NDVC planned to coordinate with Department of Mineral Resources, Thailand Meteorological Department, and relevant agencies such as Pacific Disaster Center and academic institutions to conduct vulnerability assessment of selected major cities in Thailand. This has not been made as planned. The NDVC planned to coordinate with DDPM and the relevant departments to implement earthquake early warning and mitigation system, preparedness and response plans at all levels. this has not been made as planned. The ANDP NDVC, Foundation of National Disaster Warning Center, IOI, relevant interagency governmental departments and academic institutions would like to establish a Teams Thailand chapter in cooperation with Teams headquarters. However, this has neither been made as planned. And then I'd like to move over to the earthquake on the 28th of March 2025. After 14 years of our workshop in 2011, the disaster had actually happened, as we predicted. A powerful 7.7 magnitude earthquake struck central Myanmar on Friday, March 28, triggered widespread panic and destruction. People fled buildings as the ground shook, with tremors felt not just in Myanmar, but also in Thailand and part of China. The Myanmar government declared a state of emergency in affected regions and states, including Nay Pyi Da and Mandalay, and made rare requests for international humanitarian aid. Thailand's capital Bangkok was declared a disaster area where rescue workers were racing to free more than 100 trapped workers after an under construction skyscraper collapsed. The Prime Minister of Thailand called for an immediate meeting on the 29th of March 2025 of relevant authorities to discuss on emergency management action taken by responsible agency, namely Thai Meteorological Department, Department of Disaster Prevention and Mitigation, the National Broadcasting and Telecommunication Commission, and others. Some gaps were discussed, which were such as slow action on public warning and limitation of operation for preparedness and response. So, what lessons learned do we have from the 28th March earthquake? We were not well prepared. Response and coordination to the distant large earthquake in Bangkok among key responsible agencies. Public communication in time of crisis was slow and ineffective. It is therefore a great opportunity to organize this follow-up workshop to review, update, and consider risk assessment on seismic hazards in Bangkok from distant large earthquake and the interpretation of recorded ground motion, lessons learned from the recent earthquakes, enhancing building codes, public awareness and retrofitting, and strengthening emergency preparedness and response, and not at least early warning system. Last but not least, I wish the workshop can provide you with forward-looking strategy on dealing with potential future earthquake. This is to ultimately save life and properties of the Thai people. Thank you, and I wish a great workshop. Bye.
Also, so that we can continue this discussion. We only have a short period of time, so I would like to continue without any break in the room. Okay, so thank you so much, President of ASA, and now I'm going to the next session. Thank you very much. Thank you. I would like to invite Associate Professor Dr. Tirapan on Thamarat to be with me at this table, please. May I introduce him again? Associate Professor Dr. Tirapan on Thamarat, Department of Civil Environmental Engineering, Faculty of Engineering, Mahidol University. He was with us 14 years ago at the conference mentioned by the team president. And at that time, I think that you worked with RIMES. RIMES, which is the Regional Integrated Multi-Hazard Early Warning System for Africa and Asia, based at the Asian Institute of Technology. And he kindly also engaged actively with our 2011 conference. Now he kindly accepted to come to this workshop. And he is going to present on the latest data and models for assessing earthquake risk in Bangkok, considering distant large earthquakes. May I invite you to kindly present? You have altogether 30 minutes, but you may present 15 minutes with leaving time for question and answer for another 15 minutes, please.
Hello. Okay. Okay, good morning everybody. So I would like to start my presentation. Maybe it is going to be a little bit technical, but I hope everyone in this room can follow me. So on the slide, the first slide, I show you the ground motion that we record from the earthquake. So the blue one and the green one is the one that record not so far from the earthquake. But the red one is the one that in earthquake engineering we know very well. That one is recorded in Mexico in 1985. That is the distant large earthquake, magnitude 8.5 at about 400 kilometers. And for engineer, we're not using only the ground motion to do the modeling of our structure. We're using the response spectrum that is on the right. On the right, that is the response spectrum for each ground motion that you've seen on the left. So you can see that the distant large earthquake, the response spectrum is in the red line. So it's quite different from the usual one. So this is what we expect for Bangkok also for many years. And our team has been trying to develop the seismic design code for Bangkok, consider this one also. So I'm going to explain you the seismic design code that we developed for Bangkok, and then what we observed from last month earthquake in Myanmar, what we observed in Bangkok, and how it compared with our seismic design code. So we're going to the history first for the seismic hazard in Bangkok. This is the one that we have been waiting for a long time, the event last month. This is the Royal Archive. They state that in 1930, in Bangkok, we felt the earthquake, but we don't know where it is. At that time, it's like almost 100 years ago. In Bangkok, we did not have high-rise building. We have only like small building, and the people in Bangkok can feel it quite strongly. Like they're causing alarm to the people, and people run from their house into the street. So it's exactly what we observed last month. So it's not it's not something that we not expect. We expect this kind of event, but the thing is that we cannot tell when it's going to happen, but we know it's going to come. And the 1930, 5th May, this is the event in Myanmar, 7.3 in Bago, along the sky fault. That is very similar to this event also, but from different segments of the same fault. So this is our design standard. We have been developing for many years, and the latest one is 2018. And this one we adopt the code based on ASCE, and we have giving the design value for the engineer for every district in Thailand, also including Bangkok. And this is the earthquake hazard model for Thailand. We have been studied the hazard model for Thailand for some time. Like we know that in and around Thailand we have a lot of seismic city, and we also have a lot of active fault. The active fault that has the large slip rate, it means that it's going to occur very often. Like it will be the red line in this region, it will be sky fault. And also, we also have another active fault very close, not so close, 150 kilometers from Bangkok. That one is Three Pagoda Fault. And then we can observe that SDA, that is the subduction zone earthquake, that in the past, it produced magnitude 8 also in Bangkok. In Bangkok at that time, people might not feel it because Bangkok just 200 years. So that event like 260 years ago. So at that time, there is no record of this event in Bangkok. So what I'm going to say is that we have the model, try to assess seismic hazard in Thailand. And then this is the result. So we know that Bangkok is not so, had a high hazard from the earthquake, but this one from the, we need to say that the model that we did is based on rock. We did not consider soft soil yet. So when we consider soft soil, the effect would be a little bit different. But we can see that in Thailand, the highest hazard zone is in the northern and in the western part. But this map still not consider the soft soil. So we're going to talk about it later. But you can see very clear that the effect from the sky fault is really high. This map shows you the return period of about 2,475 years. So we know that the earthquake, the big earthquake from Myanmar along this sky fault going to come. And this is the major city in northern Southeast Asia that have different seismic hazard, like in the red line that is Naypyidaw, and then on the blue line is Mandalay. So at the same hazard, we expect that Naypyidaw and Mandalay would have the highest seismic hazard, mostly from the sky fault. And other major cities in northern Southeast Asia also have different distribution of the hazard. And when we do the aggregation means when we know what is the level of the hazard, we want to know what causing the earthquake that's going to cause the hazard. So this graph might be a little bit difficult for you to understand, but I would explain. On one side, you will see the magnitude. Another side, on the X, you will see the distance. So for Mandalay and Yangon, the hazard mostly come from magnitude, large magnitude earthquake, like magnitude 7. Distance is very short. That is what we expect from sky fault. But if we look for other city like Bangkok, like on the bottom, you see that for the peak ground acceleration and spectrum acceleration, it always comes from distant earthquake. So based on our model, we know that the hazard for earthquake in Bangkok is going to come from distant large earthquake. It's not going to be the earthquake that small or large inside Bangkok, because Bangkok we did not have the active fault. So when we know this, this is the hazard that we should be considered in the model. So what did we do when we try to give the seismic design code for the engineer? So we need, but before going to that, I would like to take some time to talk about the one that we still afraid that it's going to occur. So the first one is sky fault that already occurred, the 7.7. Another one is Kanchanaburi, that is Tri Pagoda fault. The one that we think that might have the potential, the subduction zone in Myanmar. In the past, there is a record in 1762. It generated magnitude greater than 8.5. And some study they found that the recurrent interval is about 500 or 700 years. And the distance from this subduction zone to Bangkok is about 700 to 900 kilometers. And this is the evidence that they did do the field work. They go to the coastal area, and then they found that there is the uplift oyster reef that has been uplift due to the earthquake in the 1762. And the uplift is about 1 to 6 meters. So if we consider this one caused by that earthquake, and then they do the carbon dating, and the carbon dating also show that this is also at the same time that have been historical record. So it is confirmed that the subduction zone is there, and it's still quiet. It not reached its recurrent interval yet, but that is the thing that we understand that the Bangkok should be considered when we do the seismic design. So when we do the seismic design code, engineer usually using response spectrum, and different response spectrum going to cause the vibration to different structure. Like for the short period, it would cause large vibration for the small building, but at the long period, like 1 second, 2 seconds, and 3 seconds, it would cause the vibration on the tall building. So for 1 or 2 or 3 seconds, this is the distant large earthquake, like subduction zone earthquake. And then we select the ground motion that fit well with the one that we consider would be like magnitude 8 at distance around 7 or 800 kilometers away. So this is the one that we use to develop the Bangkok seismic design code. And this is the response spectrum from the ground motion that we think that it could have impact in Bangkok, but this one is on the rock. After that, we do the measurement for the shear wave velocity in Bangkok, and then we do the ground response analysis to consider the soil amplification. So this one is on the bedrock, and then it has been amplified by using the data that we have. So the ground motion in Bangkok has been amplified due to the soil model that we have. And then this is the input ground motion on the rock, and this is the amplified ground motion. So this one is the one that we have been studied, and then we use it in order to tell the engineer that this is the level of the design that you should use. And this is the blue line is the average. That is the value that engineer has been asked to design according to our seismic design code. Well, when we publish this one, a lot of engineers asking that how reasonable of this seismic design spectrum, because it's quite large, and people out in Bangkok did not feel earthquake that often. So there is some resistance and engineers start to question more when they need to put more reinforcement into the structure. But anyway, this is the seismic design code in around Bangkok area. We put in different zone, and for the downtown of the Bangkok is zone 5. So it's quite different spectrum. Like if you consider normal spectrum from the textbook, it would be like very high value at a short period. But you can see that the seismic design for Bangkok is they're going to amplify the long period like 1 sec, 2 sec, or 3 sec. So it is quite unusual spectrum compared to the design spectrum for many places around the world. Okay, so let's talk about last month earthquake and then what we observed from the record that we have, and then let's compare with our seismic design spectrum. So luckily in Bangkok, we have a number of seismic stations operated by Thai Meteorological Department. And I would like to compare this spectrum with the one that we have stationed in Kanchanaburi. Kanchanaburi is the station on rock. So the difference between the basin. So what you see, the purple line is the elevation model. So you can see that in the central plain of Bangkok, no, in Thailand, is the low-lying plain. That is the sedimentary basin. So outside Bangkok, that is Kanchanaburi, that is some kind like outside the basin already. So we're going to compare the effect of the basin and without the basin. So this is the ground motion that we record in Kanchanaburi. We plot on the same scale, and this one is recorded in Bangkok. So you can see that the peak ground acceleration in Kanchanaburi is just 0.006 G, very low. But in Bangkok, it go to 0.02 G. So the amplification is real. We see the amplification about 3 times. But not only that, for the duration in Kanchanaburi is just about 40 seconds. But in Bangkok, we see the amplification about duration is about 150 seconds. So Bangkok is farther from the earthquake, but we feel larger ground motion. Not only larger ground motion, we feel it longer. That is the perfect storm for the tall building. So we see the soil amplification 3 times in Bangkok Basin, and we see the signification duration about 4 times. So the basin not only amplify the ground motion, but it also make the ground motion become longer. And luckily we have station inside Bangkok, and then this station can record the peak ground acceleration mostly consistently about 0.02 G. There's one station is quite low, maybe there's malfunctioning. We need to do more investigation. And this is the ground motion that we observe in Bangkok, and this graph we call spectrogram. Spectrogram will show you the energy content. So this one is about 1 Hertz, and this one is about 0.1 Hertz. So it's about 1 sec to 10 sec. That is the fundamental period of the tall building. And we can see that when the peak come here, you can see large red energy here. So it means that the ground motion in Bangkok, when it amplifies, it causes a long period energy that matches with the tall building. So that is confirmed what we are afraid, that the ground motion in Bangkok would be amplified by the basin effect. And then if we look closely, you can see this is the body wave. It comes something like 2 minutes after or 3 minutes after the earthquake. And the one that caused last sway in Bangkok is the surface wave. It comes about 4 to 5 minutes after the earthquake. So Bangkok, if we develop the earthquake early warning system, we can have a high chance that we can succeed, that we can warn the people in Bangkok maybe 2 minutes. So we can reduce the sky train speed or prevent people to using the lift. So this one is the one that maybe we can improve in the future. And I just want you to see more closely, like this is the station that we can record in Bangkok. This is the north, south, east, west, and vertical. So we did not see much the large amplitude in the vertical direction, but we see much in the horizontal direction. And the duration is quite long. And this one is record on the ground. So it means that if you're on the ground in Bangkok on that day, you would feel the large shaking about 3 minutes. But if you're on a high-rise building, you might feel longer and stronger than this. So if you go back to the comparison with the USGS, 0.02G, you might feel like MMI 4. Then you might feel a little bit dizzy if you stand on the ground. And this one is the peak ground velocity. So we usually compare the damage with the velocity. And for the velocity, we see it about, for the north-south, 10 centimeters per second. East-west also. But for the vertical, it's a little bit lower. For the MMI, it would be 5. So people might feel quite strong for these earthquake. Well, it the same like what we have been reading, right? From the history, like in 1930, they must feel the same thing like what we feel last month. And this is from another station, also the same, like the graph is consistent. It have the long duration, almost 3 minutes. And the peak ground acceleration also the same, like 0.02G. And this one is peak ground velocity, the same. And if we using the data from the USGS, they also say that inside Bangkok area, they feel about MMI 5, and outside it, they feel about 4. So this is the record, and then the intensity of the people feeling the same. So this is confirmed. And now I come back to the response spectrum. This is the response spectrum for 5% damping, the red one. And this is the seismic design spectrum that we give to the engineer for the design. So luckily, for the 20 to 50 story building, you see that it's still like 1/3 what we give to the engineer for the design. But actually, someone might say for the tall building in the code, they also said you damping, it should be lower, so it's about 2.5%. So the design value for the damping for the tall building, it should be higher. And when we plot the 2.5% damping, it's also quite high, like it almost touching the design. So I would say that most of the tall building in Bangkok, if designed correctly following the seismic design code, should not have much damage to the structural part, but they might have some damage to the non-structural part, like the cracking of the infill wall, but the structural part should be safe. Because when we look at the value, it's still below, but it looks quite too close. After this earthquake, we have a lot of data. So maybe in the future, we're going to improve our seismic design code again. We have to revise it based on the new information that we have. Because in some building, like tall building, we do install the instrument in some tall building, and the damping could be around 1% also. So we might need to have the new spectrum for 1% high-rise building. And also, we might need to extend our spectrum to be more than 6 sec, because currently we can just provide until 6 sec, but we see the amplification at 6 sec also. This is the east-west direction. This is the north-south direction. So we can see that the north-south direction is larger than the east-west direction. Well, we still study more, but we're thinking that because the rupture from the north-south, from the north to the south, so they might have some directivity effect. And actually, the thing is that inside Bangkok, we have some study in the past. For the one here located in central Bangkok, this graph shows you the shear wave velocity. We see that inside Bangkok, in the central business district, the depth to the bedrock is quite deep, maybe 900 meters. But outside Bangkok, maybe something like in Pathum Thani, the depth to the bedrock is about 600 meters. So the depth is vary. And the depth vary also controlling the fundamental period of the basin. Like this is in Pathum Thani, you can see that the zigzag is quite low. And then the amplification for different damping also quite low compared to the one inside Bangkok. So this one is the one that we're going to study further, that maybe there is some difference in amplification at different locations also. This one is in the north-south, this one is in the east-west. And this is the comparison for different stations. It looks more or less the same, but everything still under the seismic design code, except in the long period that we not have much like more than 90-story building. So to sum it up, I would say that Bangkok seismic hazard for high-rise building is controlled by large and distant earthquake. And Bangkok seismic station amplify both amplitude and the duration compared to the station outside the basin. And most long period energy content located when the surface wave arrive. The high spectrum acceleration could be observed at low damping, like for the tall building, like 2.5 or 1%. Then we need to revise the seismic design code again. And station located in the deepest part of the Bangkok basin show long period amplification also. So this one going to be the one that we need to do more to protect our tall building in Bangkok. Thank you.
Thank you very much, Professor Thirapan. You have provided in-depth mechanism of earthquake and very interesting. So I'd like to now open the floor to participants for any few questions and answer, please. Maybe we need a microphone for them. Any question can be asked, technical or simple question, please, to make you understand about what happened to the Mandalay earthquake. And this is opportunity, please. Any question will do. Okay. No. This one.
Hello. Oh. Thank you very much. A very fascinating presentation. I think you said the building codes had been, the latest ones were from 2018, is that right? And then you're looking to revise them again. Do you have an understanding of what percentage of the high-rise buildings in Bangkok were built before that time? So to what percentage are to the latest codes?
So the revision of the seismic design code in Bangkok have been done like 3 steps, as far as I know. In 2018, that is the latest one that we have issued. Previously, we did that in 2010. And when we compare the 2010 and 2018, the seismic design spectrum is more or less the same for the tall building. But it has, for the 2018, we make it increasing for the small building also. That is, so I would say that the seismic design code for the tall building in Bangkok has been implemented since 2010. Before that, we also had the seismic design code in Bangkok, but we must say that it has not been strict like current design code. But before that, there not much tall building in Bangkok. And I think at that time, like 20 or 30 years ago, the reason that a lot of tall buildings still survive from this earthquake is because at that time, the typical plan has been designed quite well. I mean, it's quite symmetric, and then there might be some consideration of the wind load a little bit. So that's why a lot of, well, when we looking about this earthquake, a lot of people just looking at one building that collapsed. That is still under construction also, I would say. I would say that a lot of buildings do survive, also the tall building. But of course, we still have a lot of work to do. We still have old building that need to be retrofit, to be strengthened like the new code. And for the future building, we might need to have the new strategy also. Like we might need to put a damper on a tall building. That is the one that we observed from our colleague in Japan. After the 2011 earthquake, they do put a lot of damper in the tall building in Tokyo. So that might be the future direction that we need to do also, like keep retrofitting the tall building and keep improving our seismic design code. Thank you.
Yes. Any other question, please? Please also introduce yourself shortly.
Thank you very much for a very interesting presentation. I just have one question. You said tall buildings are 3 times sort of greater to be effective, but it would not be structural damages. Could you please elaborate a little bit on that? Thank you.
Well, I would say that for engineer, especially for earthquake engineer, when we asking the designer to design the structure, we know that the return period for the large earthquake would not be that often. It would be very long until it occurs. So if we're going to ask the engineer to design very strong structure, that would cost a lot of money. Something like you would not see the column like you would see very large column, large shear wall, and that one would cost a lot of money. I mean, who's going to be able to pay for that? So in the seismic design code, we would allow some damage occur to the structure, especially for the non-structural part, because those part is not structural part. It's going to be like changed during the lifetime of the structure anyway, like the infill wall. Maybe you're going to change the location of your infill wall, so the engineer did not give much consideration on that. We put much consideration on the structural part. But for the non-structural part, we thinking that could be okay if it damaged. But the most important thing is that the building should not collapse. That is the main goal. But I understand that for some building, that is very important building, non-structural part is really important for their functioning also, like the hospital. If the ceiling has been damaged, like falling down, the hospital might not be functioning. So maybe that is the future direction also, that we need to strengthen the non-structural for important building that going to be used after the earthquake. that need to consider it during the seismic design also. Thank you.
Thank you very much. I'd like to ask for the last question, if anyone wants. If not, I'd like to mention that I'm going to request a PowerPoint presentation from speaker. We will provide to the participant in PDF. Okay. Secondly, any more question can be sent to me, and I will forward to Professor Thirapan. And lastly, the minute of the meeting will be provided after approval by each speaker. In fact, I have a draft minute already, a structure. Thank you very much, Professor Thirapan on Thamarat, for your kind contribution, and we look forward to work with you in the next meetings. Thank you so much. Thank you. The next speaker will be online. It will be on the analysis of recent earthquakes in Myanmar and Thailand, implication for disaster preparedness, and it will be presented by Dr. Walter Mooney, United States Geological Survey of USA. May I kindly invite Dr. Walter Mooney, if he is available now. What time is in USA at the moment, USGS? Do you hear me, Dr. Mooney? You may have to turn on your microphone. Your microphone, please. We do not hear you. Do you hear me?
I think now it's working.
Okay, thank you. Thank you. What time is it now in USA?
Oh, it's not too bad. It is 11:15.
Quarter to
And
11.
I think you can see my slides now. Is that okay?
Yes.
Good, thank you. So, ladies and gentlemen, it's my pleasure to address this audience and to tell you about the recent earthquake that happened in Myanmar. This magnitude 7.7 earthquake, as you know, was devastating. I'd like to acknowledge Chesmir Verapat for the organization of this meeting, which is very important and time-consuming, and also the Association of CME's Architects for your interest. Now, we look very carefully at the data collected from the Thai Meteorological Department. So we want to acknowledge the Director General and the Earthquake Observation Division of the TMD, who provide the basic data that we require to understand these kind of earthquakes. So what about this recent earthquake? Well, you know very well where it's located in central Myanmar on the Sagenga Fault, right in the middle of Burma, in between the Shan Plateau and the Burma Block. The location is also a region surrounded by active faults, including those that are building the modern day Himalaya. So unlike Bangkok, which is very stable and quiet, the region of the Sagaing Fault is quite active. We will see this location map probably several times because it's an excellent summary by Wang et al. From 2014, showing in blue the Sagaing Fault and in red some of the surrounding faults. So what's going on here? Why do we have such strong earthquakes at this location? As you will recall from your studies and your reading, India is moving north into Asia and colliding to build the Himalayan mountains and the Tibetan plateau, while China and Thailand are moving to the south. And the Sagaing Fault is the strike slip fault that accommodates for the motion between India and South Asia. So it's a very important fault. It's a fundamental fault. It's a very active fault with constant buildup of strain. Let's take a look a little bit closer at this fault where it occupies central Burma. Here we see a pretty complicated diagram with the Indo-Burma range off to the west, the Burma Basin in the center of the image, and the Sagaing Fault on the east side. The rupture is shown in red. One of the reasons why this fault and this earthquake was so damaging was that it occurred in a very highly populated region, a very relatively flat-lying agricultural region with a big population density. So the fault rupture is shown in red and extends for about 400 kilometers. Oh, let me go back. So the Sagaing Fault has a buildup of strain of 20 to 23 millimeters a year. Let's put that into normal, simple terms, about 2 centimeters a year. That means that in 200 years, there will be an accumulation of earthquake strain that will reach 400 centimeters, that is 4 meters. That's enough to create a magnitude 7.7 earthquake, 4 meters of slip on an important fault. This is exactly what happened on March 28, 2025. We can see this fault very easily from Landsat satellite imagery. Notice the trace in the middle of the image. To the east, the land looks quite different, a lot greener, a lot more vegetation. And to the west, a different kind of geology because the fault has moved these different respective geologic blocks many hundreds of kilometers. Even the river, you can see the river, how the river it used to flow to the south, but on the west side, it's been transported to the north, and it makes a bend as it goes across the fault. So here is this, again, fault. As I say, even an amateur geologist can identify this and would immediately recognize it as an earthquake fault with a very high potential and very great hazard to the local population. So the cause of this earthquake is well understood. The hazard posed by the central Sagaing Fault has long been known to earth scientists and was widely reported. It showed up very clearly in the earthquake hazard map of the previous speaker, who it showed up as a very bright red patch in his presentation as well. So this is what happened during this earthquake. It initiated near the city of Mandalay. We call that the epicenter, but that is not where all the damage occurs. The earthquake had a long rupture and ruptured along the Sagaing Fault for 400 kilometers to the south, approaching closer to Bangkok, a lot closer than the epicentral region. So the epicenter is just the initiation of the earthquake. It's not the whole earthquake by any means. So the consequences are well known to all of you. And those of you who have gone to visit post-earthquake, who've conducted post-earthquake surveys, recognize this kind of damage and the engineering problems that give rise to pancaking of floors and so on. This is not my topic today. I will not talk about the structural problems. 24 hours after the earthquake occurred, or actually probably 12 hours, the USGS issued an estimate of the fatalities. USGS estimate was over 10,000 fatalities from this earthquake, between 10,000 and 100,000. Sometimes these slides. So far, the reports that have been published in Burma, in Myanmar, list 5,370 fatalities. I cannot say with any assurance, but it seems possible, perhaps even likely, that this number is currently is an underestimate, and the total number will be in excess of 10,000, unfortunately. Economic losses, USGS estimated anywhere between 10 billion and $100 billion in losses. So conclusion number 3 from USGS side is that the estimated fatalities and economic losses may be revised upward in the future. The estimates that I'm reporting to you today are based on the current news that we are able to obtain from Myanmar. Well, this is a pretty active seismic zone. Don't worry, you don't have to follow all the details of this figure whatsoever. This showing in yellow the shallow earthquakes, in red the deep earthquakes. Let's take a zoom in and look a little bit more closely. What we notice here is in this red circle, a vertical north-south line, that's the Sagaing Fault, and there are relatively few earthquakes occurring in this red circle, much, much fewer than occur to the south of the circle or to the north. So this portion of the fault has not been slipping, and the stress has been building for many years. As you'll see, I'll estimate that the number of years is about 186 years. Stress has been building. So the few earthquakes in the central Sagaing Fault prior to March 28, 2025. Now, geologists look very carefully at the geometry and location of a long fault, this one being well over 1,000 kilometers long, and we'll divide it into segments. And here are the segments from Wang et al. In the boxes are the names of each segment. There are about 10 of them. And what we're talking about today is the Miktila segment, which the Wang et al. Estimated had a potential of having an earthquake of magnitude 7.8 to 7.9. Now, I just showed you the calculation that indicated that about 4 meters of slip could occur in a period if the fault was quiet for 200 years. So this is now the time scale of the different earthquakes. Let me explain this. Time goes back in time on this horizontal axis. So 2012 is here, 1956, and 1839 goes back. And you'll notice that there's a gap here in earthquakes in the region of the central Sagaing Fault. So here, in this portion of the fault, there had been an earthquake in 1929 to the south and to the north in 1956, but in the middle, there was an earthquake gap. And the previous earthquake had been 1839 or 1837, about 190 years ago. Well, we can use round numbers, about 200 years of no earthquake on this central portion of the fault. So this was a clear gap in seismic activity, and was predicted to generate an earthquake of about what we got, about 7.7. So conclusion number 4, earthquakes cannot be predicted. However, earthquake probabilities can be calculated from scientific data. An earthquake prediction is the time and place and magnitude precisely. Earthquake probability is the probabilistic description of the likelihood in a general period of time for the earthquake to occur. And Wang et al. 2014 correctly forecast the long-term probability of a future large earthquake on the central Sagaing Fault. So we're doing our job. Who's we? We're geologists, earthquake geologists, geophysicists, geodesists, the earth sciences. People are doing their job and talking to each other and are able to identify likely locations for strong earthquakes. So let's take a look at what this earthquake rupture looked like, because what I'm about to show you has a lot to say about what happened in Bangkok, what was experienced in Bangkok, and indeed in Myanmar. So we're going to look at the rupture. So we're going to look into the earth like slicing a cake, and we're going to look at the surface of the fault that moved during the earthquake. So we're opening the earth, we're slicing into the earth and looking at the fault surface. So here it is. The horizontal axis is depth into the earth from 0 to 15 kilometers. That's the vertical axis. The horizontal axis is distance from the hypocenter. Hypo means under. Oh, I misspelled it. Hypocenter. I should check my spelling. And the location of the earthquake is here to the north. The dark colors are the patches of the fault that had strong slip, large, high magnitude slip. 4.5 meters was the maximum. So as you can see, although the earthquake began in Myanmar, it propagated to the north for about 75 kilometers, and it propagated to the south for about 400 kilometers with very strong slip at 200 kilometers away. Now I'll show this on top of the earth, and you'll have to use your imagination to see what it means. So here's the earthquake hypocenter. That's the buried earthquake source. The earthquake ruptured in two directions. We call this a bilateral earthquake. It ruptured very strongly to the north for about 75 kilometers, and it also propagated all the way to the south for about 400 kilometers in the direction of Bangkok. So the previous speaker mentioned what we call the directivity effect. If the rupture is propagating to the south, there'll be a buildup of energy in the southerly direction, and this would amplify the earthquake ground motion. So the March 28, 2025 Myanmar earthquake is not a point. It's not a point on the Earth's surface. It's in fact an earthquake fault that ruptured 400 plus 75 to the north, about 500 kilometers. It's a very big and extensive fault. So what about the ground shaking? Well, we geophysicists like to believe that we can predict pretty well the intensity of ground shaking as a function of distance. And here is a curve with the observations collected by USGS in purple and red, and the expected curve, which, as you can see, is well below the observed curve. So these observations of intensity 8.5 and 8 and 6 and 7 are well above the orange or green curve, two theoretical curves, as you can see here. The reason for this is exactly the same as the diagram that I was just showing you. The earthquake rupture extended so long that even at 100 kilometers or 200 kilometers away from the hypocenter, the ground motion was very strong because the earthquake rupture was nearby these observation points. So the extended length of the earthquake is the reason for the misfit between the theoretical calculation, which is a simple model, versus what happened in Myanmar with this unusually ultra-long rupture. And it extended the strong intensity and the strong motion over the length of this fault, causing widespread destruction. So this is a quite unique earthquake by virtue of its length of rupture. So the south end of the rupture is only 600 kilometers from Bangkok. And Chiang Mai is not labeled here, but it's near the letter F from. Chiang Mai is about here. And Bangkok is not located 1,000 kilometers from this earthquake. Bangkok is only 600 kilometers from the southern end of the earthquake, so it's much closer. This explains why the damage was so strong in Thailand, in northern Thailand, and indeed in Bangkok, as we just heard from the previous speaker. So we have an ultra-long rupture and a large amount of slip, 4 meters on parts of the fault, all of which conspire to make a really dangerous and catastrophic earthquake. The damage you have seen in the newspaper and in your own research, you can look at just even looking at these photos, it's a giveaway what are some of the problems in the construction with just masonry with a minor amount of rebar, and in this picture on the right, soft first story, the entire building apparently being held up by small columns that were not adequate for the task. Thank you very much. This is my summary of the earthquake, what happened, and why we experienced what we did. And I'd be delighted to take your questions.
Thank you very much, Dr. Walter Mooney. I think we are able to take some questions, please. Nobody asked. Let me ask you. May I ask Dr. Mooney on future cooperation after the Mandalay earthquake? What are needed in terms of capacity building in Thailand and other countries? How can USGS collaborate with us, with team or with any partners to do this kind of capacity building?
Yeah, I would say that like the recent earthquake in Myanmar, we find something unusual, something unexpected for every earthquake. The intensity distance curves don't fit, as I showed, because the earthquake rupture was so long and the amount of slip was so great. So the main task at hand is to share our knowledge, share our recordings, and share the data that we have. The previous speaker showed us, for example, the experience from the Mexico City earthquake, so-called Mexico City earthquake, the ground shaking that occurred in the basin of Mexico, which is very comparable to the amplification that we see in Bangkok. So I would say sharing experience, our knowledge, and the data that's recorded. I'm old enough to remember when one strong motion recording one good recording of an earthquake was considered to be something very valuable because there were very, very few accelerometers. And I can remember when there were very few buildings that had multiple, that were instrumented, that had accelerometers on the top, middle, and lower floor. Today, we have many such buildings that are instrumented, and we can learn a lot about the response of these buildings by sharing the data. And this is something that USGS would be very happy to promote, to facilitate, and to participate in.
Question. You mentioned that earthquake cannot be predicted. And you say that a group of scientists, Wang et al., in 2014, correctly forecast long-term probability of magnitude of 7.7 to 7.8 of Sagang fault. Will this be possible that USGS compile this kind of forecasting with the active faults in this region and probably provide some kind of suggestion on what might happen and call for preparedness from a country in this region?
It's a very good suggestion, and the recent earthquake has heightened everyone's and determination to share the information. As you saw in northern Thailand and Myanmar, there are a great number of faults. We have today been talking about, the biggest one, the biggest and the most evident one. However, in the hazard map shown by the previous speaker, there are other potential faults. And I think collaboration between Thailand and USGS to identify these and to assess their potential, hazard potential, would be time very well spent and would be very welcomed by the USGS.
Thank you so much. There's one question, please.
My name is Sopapat Komanman, TMC Asia. I would like to ask you about the prediction that you mentioned that it's difficult to predict. So what about another or new technology about quantum technology, which is a quantum sensor or quantum radar, quantum communication, quantum key distribution? Is it possible to, in the near future, maybe we can use technology to prediction? Thank you.
Yes, I agree. This is a very good question. We're only now beginning to appreciate the power and the change that the new technology like quantum computing and machine learning will bring. And, with quantum computing and machine learning and artificial intelligence, the machine can consider every earthquake that has occurred and every fault and make associations and computations that an individual scientist might not be able to make. So the future is looking bright, and many people share the optimism that at least for specific faults, not for every fault and not for every situation, there will be progress in this field. But I would like to ask you a question just to respond. What about quantum computing and machine learning? Will there be a future for architecture? Maybe in the future, architects can be replaced by a computer.
Maybe can ask Vice President answer?
Thank you for your question. I'm Repan Shinawat, Vice President of the Association of Chinese Architects. To answer your question is actually it's not the main point of design of architectures, but we have to follow the rules and the structural engineers, and we have to consult together. And about the computing calculation things, I think we have to sit down together with the structural engineers and the other discipline to discuss about this. So alone, we cannot doing the computation things about the earthquakes design only. So I think this is a good question to raise awareness about the design session for the earthquake for the building in the futures for Thailand. Yes, thank you.
Thank you very much, Vice President Veerapan Shinawat. This question may be inserted into this afternoon session. Okay, all right. Thank you so much, Dr. Muni, for your great contribution, and I hope that your proposal for collaboration with Thailand to proceed further with any kind of capacity building or collaboration will be recorded, and so we look forward to work with you in the future. Thank you very much.
Thank you.
The next speaker will talk about improving early warning system and communication protocol. It will be presented by Mr. Jintanadilok, Section Director of Academic for Disaster Warning, Thailand National Disaster Warning Center, NDWC. May I invite Mr. Jintanadilok, please. I'd like to mention that I used to work at NDWC in the aftermath of tsunamis, and now we leave all the works to the new generation, and Director is the generation responsible for the increase of disaster, and I would like to thank him for contribution.
Thank you. Good morning, everyone, again. First, I have to apologize about my English. I don't use this often. First, I want to talk about the disaster management system in Thailand. We work under the 2007 Disaster Prevention and Mitigation Act. And we have a national plan of disaster prevention and mitigation 2021 to 2027. And we have a policy maker, the policy committee. It's called the National Committee on Disaster Prevention and Mitigation. We work with disaster risk management as a operation unit. We do all the things of the circle before when the disaster occur and after the disaster. We do the prevention and mitigation preparedness and do the response and relief and the rehabilitation and reconstruction. At my part, I work at National Disaster Warning Center. It is on the preparedness and prevention and mitigation part. DDPM, we work with seven hazards. The first one is tsunami. That is the beginner of the NDWC in Thailand. The tsunami on 2004. 2004. Yeah. And then the second one is the earthquake. We received the information from TMD, the Earthquake Observation Division. And the third one is storm. We also received from the TMD. Flood, we received from the another agency, landslide also. And for the coal and PM 2.5, this is the part that we have to inform the people to aware. Our operation, we have three parts of operation. The first one is gathering information from every agency in Thailand and from abroad. The second one, we have to analyze the information we get. And if it's possible to be a disaster, we have to dissemination the warning to people. In disaster prevention and mitigation plan, we have 5 levels of warning. We separate it with the color. The first one is green. It means the emergency situation. It is advised to keep track on relevant information on regular basis. The second one is blue. The blue is mean the situation where activation of disaster surveillance system is needed. Take all required steps to closely keep track on disaster information on and 24 hours basic. The yellow one is mean the situation has been increased likelihood of hazard event. It is advised to be prepared to cope with potential disaster and to conform to the current advice. The orange one is mean its likelihood hazard is imminent. The government officials are attempting to bring emergency situation under control, take immediate action to evacuate, to design a safety place and follow the guidelines set front. And the red one is the hazard event is most imminent. It is recommended to remain or stay in completely safe place and follow the advice or instruction of the authorities. In this case, it's like tsunami. Slide ไม่เลื่อนครับ We have so many channels to disseminate the message to the people. We have our own equipment. The first one is the warning tower. This tower can disseminate the alarm about 1.5 kilometers to 2 kilometers far. The second one is EVAP, or you can call it warning box set. We set this box at the Provincial Disaster Prevention and Mitigation Office and Thailand radio station, Province Thailand radio station. But if we announce the message to this box, the official receive the message will extend the message to the people in the area. And the third and the fourth one, it combined together. CSE radio relay station, it received the message from the center, NDWC, and disseminate with the radio frequency to the small warning tower that can disseminate the warning about 1 kilometer far. Yeah. And we have a channel like BUS. BUS is broadcast alerting system. We send the message to 17 digital TV station and three radio station. And we have application like Thai Disaster Alert and Line Official. And we try to disseminate the warning through the social media like X and Facebook. And the next step of warning, we ongoing to use the cell broadcast system, and it will complete in July this year. Yeah. Next, for the community-based disaster preparedness program, in this title, there is 4 components of this. The first one, the risk knowledge. In the different area, there is a different risk. People in their own area, they have to know what they have to face of the hazard. And if they know what they have to face off, they have to monitoring and forecasting. If it has likely to be a hazard or likely to be a disaster, they're going to disseminate the warning to the people in that area. And the most important thing is the public awareness and response capability. The 3 above, the 3 above will not in vain if the people not awareness the warning from the government or the local government. Okay, let's talk about the situation on 28 March this year. Everyone know that have an earthquake on Myanmar, 7.7 magnitude. In our department in Bangkok, in that time, I feel a little bit dizzy and feel like going to faint. And I don't know what is going on, but when I turned back, I saw our colleague walking and running. Okay, I think something happened. Oh, it's an earthquake. First thing, I know that if you in the building, you have to cover your head or find a safety place to hide. And after the ground motion stop, you have to remove yourself out of the building. But in that day, I walk with them and run, because this is the gap of the earthquake in Bangkok, because people don't used to face up some kind of this event. They don't know what to do, even myself. This is the gap that we have to improve. Yeah. After that, DDPM tried to send the SMS short message to people to make them understand what happened and what to do. But the SMS is not the appropriate channel to send to people. It's not work with the emergency situation. because it had a limitation of SMS. It can be, it can have only 70 characters, and it have a time to prepare to send to people's cell phone. Some get this message next day. Some doesn't have. Yeah. Me also. I don't have. I don't get it. I send it by myself, but I don't get it. Joking. Okay. We after that we try to improve our SOP, standard proceeding, standard operating procedure. I think before we have cell broadcast, we try to use SMS that we know that not impact, it's not effective. We think if we have cell broadcast, we will disseminate the message to people more understanding and faster in a second. Let me talk about cell broadcast. Cell broadcast is conclude with two element, conclude with two component. First is CBE, we call cell broadcast entity. This is the one who send the message like DDPM or TMD or police station. And the second one is the disseminator, is the MNO, mobile network operator. They will receive the message from the entity and spread the warning to people's cell phone. And we're going to have cell broadcast testing in three scale: small, medium, and large scale. The first one is the small scale test on to 2nd May 2025 at 1 p.m. Yeah, we will test in the building like Provincial Hall at the Chiang Rai Provincial Hall, Ubon Ratchathani Provincial Hall, Suphanburi Provincial Hall, Songkhla Provincial Hall, and Government Complex, Jang Watthana Building A and B. We will disseminate the test message to the people within the building. And the second one is the medium scale test on 7 May at the same time. We will disseminate the test message in the district area. We will send it to Mueang district of Lampang, Mueang district of Nakhon Ratchasima, Mueang district of Nakhon Sawan, Mueang district of Surat Thani, and Dindang district in Bangkok. And the last scale test on 13 May, 1 p.m. We will disseminate the test message in the boundary of province. We will send it to Chiang Mai, Udon Thani, Phra Sri Ayutthaya, Nakhon Sri Thammarat, and all over Bangkok. Yeah, people who receive the message will get the message like, this is the test message from Department of Disaster Prevention and Mitigation, DDPM, no action required. Okay, if you get the message or alarm on that day, don't panic, okay? Okay, I think this is all of my presentation. Any question you want to ask?
Thank you so much. This gives us important message from the government of Thailand, who are responsible for early warning mitigation system. So if there is any question from the floor, please, you are welcome. Yes. Microphone. Please stand here. Somebody will do it.
Thank you very much for your presentation. I was wondering, when you do the broadcast, is there a way for you to tell how many people have received the message? So if you're doing it by cell tower, how many people are in that area, to understand maybe the impacted population?
This is, I think we have to analyze the area that we think it's going to have an effect. As I say, DDPM, we receive different information from different department agency. They will
there will be a specific area.
Yeah, there will be a specific area for us.
For drill, broadcast drill.
But we have a lot of work to do about to use cell broadcast system. This is new for us and new for Thailand too. And I think this is a very big impact to people. If, as I say, if they work in the night, they have to sleep in the day, on the day. And if we use this broadcast more often and don't have anything happen, they will sue us like that.
Just to add the question to Kun Victoria about the area of, that will test the system. Will this be in different provinces, or this will be only in Bangkok?
We have 4 provinces and include Bangkok. Yeah,
other provinces?
I can show you again. Okay. In the small scale, we will test at the provincial hall at Chiang Rai, Ubon Ratchathani, Suphanburi, Songkhla, and government complex Jangwattana, building A and B. And the medium scale, we will test at Mueang district, at Lampang, Nakhon Sri Thammarat, Nakhon Sawan, Surathani, and Dindang district, Bangkok. And the last scale, we will test at Chiang Mai province, Udon Thani, Pranakon Sri Ayutthaya, Nakhon Sri Thammarat, and Bangkok. Yeah.
For example, I'm not going to be in Jangwattana on the 2nd of May. I will be in Sathorn area. Will I receive that too?
You will not receive the message.
So I have to come here?
If you want to receive the message, you have to go to...
Okay. So you are welcome to come to
Jangwattana. Yeah.
At what time?
At 1 p.m.
1 p.m.
Yeah.
So that you can test your mobile phone.
And the duration is 10 minutes long.
10 minutes.
If you get the message and you walk out of the building and you come back, you will not get the message again. And the one who not get the message will receive the message in 10 minute duration.
Okay, thank you. Any question? Yeah. If no, I ask question. You know, even though I'm not new to Teams, I just received appointment last November. But I have been working with him since after tsunami. Now I have a role to play with this organization, as I know from the president that they have a contact of around 100,000 people around the globe. And the only thing is that there is no Thailand chapter. And I'm a Thai. I'd like to establish a cooperation with NDWC to work on the Thailand chapter. There is no commitment, but that means whenever we agree to organize activities, we will do it. And because you are the government, it will be a strong position to communicate with others, stakeholders. So will you accept me to establish the chapter?
Oh, this is your question?
Yes.
In my opinion, yes.
Thank you so much. Okay, that's it. All right.
Only me.
No.
Our organization will accept
okay.
all cooperation.
Not only teams, but also other partners that NDWC always open to, and
yes.
What will benefit to save life and property of people.
Yes.
The NDWC will be responsible for.
Yes.
Thank you so much.
Thank you everyone for listening.
Thank you. Now, I'd like to proceed for the next speaker. It will be on enhancing building codes, public awareness, and retrofitting. Presentation will be made by Dr. Kit Miyamoto from Miyamoto International, United States of America and Japan, on impact of Myanmar earthquake on Bangkok and next steps. May I invite Dr. Kit Miyamoto, please.
Hi, Dr. Chasak. So nice to see you. Long time.
Yes. What time is it?
15 years. Right now it's no bad. It's not 9 o'clock here in California.
All right.
Let me show the screen. Just one second. You can see where? It's good?
It's good. Yes.
Yeah, okay. So next 20 minutes, so I'd like to talk about impact of Myanmar earthquake on the Bangkok and what's the next steps should be here. Just a little bit of our company. We are located in about 30 different locations globally. Essentially, as you can see, we are on a ring of fire. That's exactly where we are at. And we actually opened office in Bangkok 2011. I think that's the first time I met Dr. Chasak and also Dr. Mooney. You know, that we are talking about long distance earthquake then in Bangkok. And everybody thought we were crazy. So now it's, you know, it's a real things now. You know, there's something we actually talk about in this specific conference 15 years ago, actually. So we've been active since 1971 for many different places, over different 100 disasters and many earthquakes throughout the world. So that's the kind of thing we do. Now, as Dr. Mooney said, this is not a small earthquake. Magnitude 7.7 affected almost 400 kilometers long of distance and 100 kilometers wide. And so first thing we did is try use a satellite image to understand what's context of the exposure of this earthquake. So based on our analysis from not only from a satellite, but from a ground recon we did, we actually, last 2 weeks, we assessed over 100 different schools and hospitals throughout the area. There's about 15 million people was subject to strong ground motion. And there are about 500,000 buildings that are exposed. And there are mainly 1 to 2 story low-rise buildings, many houses, and they're made of either unreinforced masonry or older concrete structures. Based on the past assessment we did for area for like this one, having this type of ground motion, combination of the quantity of what's going on, and also archetypes of the building stock exist. We estimated 30% of these buildings, almost 150,000 buildings and houses, could be either collapsed or severely damaged. And additional 150,000 more sustained at moderate to slight damage. They're not habitable. So you're talking about the 60% of buildings. So which means almost 10 million people, they're not able to live in those houses. And as the Dr. Mooney said, our estimation based on this is somewhere between 10,000 to 100,000 fatalities. And this is a per USGS estimate too. That's something we see all the time. So yes, it's definitely the fatality is much higher than what's been estimated so far. So this is any means not small event. This is a big, gigantic event which affected the so many millions of people right now in Myanmar. So for this next steps, we have provided a critical infrastructure assessment with the UNOPS and also UNESCO, focus on the healthcare and the schools, and also some of private, and also understand what is the to do residential structure assessment and a communication campaign attached to that. So we have now teams deployed on the field. So let's come back to Bangkok. What's the impact here? It's Bangkok, we changed the building code in 2007 and 2017. So actually anything built before 2007 is what we call non-ductile concrete structures, which means extremely dangerous. It doesn't really consider the earthquake effect at all. After that, it got a little better. It's actually, it's not bad, but it's not great. That's why you saw some certain things happen in the city. And 2017, code really changed that to really start understanding what's the high-rise buildings, construction, and so on. But even that long-distance earthquake never been really considered. See, this is the where the you can imagine that jello, one side of a say table, long table. You shake it in the one side of a table. You can imagine the jello shakes a lot. Depends on how you shake them. And if you stick something tall, like a little chopstick, it will swing a little more. That's exactly what happened here. Here we have the almost 800 meter deep of a soft soil. That's called a soft soil. The so-called effect of this amplification of motion. That's why they use a lot of swinging and damage and collapse in high-rise buildings. And this is something that we saw in Mexico City, something, in 1986 and 2017, that distance of earthquake is really far, but it's impact quite a bit. So this kind of things happens. It's not anything special about in Bangkok, but it's something we noticed for a long time. That's why we've been talking about this long distance earthquake impacting tall buildings for quite a long time now. But there's widespread damages and collapse even in new construction. So that now there's uncertainty in a commercial residential investment, and some of the commercial banking finance has been stopped because of its perceived risk of investment to tall structures. So this is a big issue, not only affecting engineering wise, but also the investment and the whole market condition in Bangkok. So what's the next step should it look like? I think need to consider the risk reduction program, how see the risk of these high-rise buildings and how can we actually reduce risk. And but we got to make a private sector investment feasible by creating some certain liquidity in the market. We cannot just expect have the building owners to suddenly spend millions of dollars to seismic strengthening, even if they want to, because of its definitely risk exists. They are aware of it now. But if there's no money, there's no way that any private sector investment can do that. So that's very important to think about it. But to do that, I think there's definitely the cost-effective technologies out there, that's being used not only in places like Japan or US, but even not rich country like Haiti, even Nepal. They use the technology like this to make this happen. So this is one example of something we touched 15 years ago here in Bangkok. So here's the building look like this. And we had an issue with this building. It's just like actually just a lot of us what we call torsional movement, twist around a lot. So here we use the what we call seismic energy dissipators. It's essentially a shock absorbing devices. What does do is it's equivalent to your car. Your car has the springs, right, on by the wheel and has a shock absorber. So that make your driving smooth. Just think about without shock absorber, how you feel. You are going to be bouncing around. So that's the technology like that. It's been used in over 10,000 structures in Japan and many countries. So here, what's about dampers is here's what you're looking here. One on the left side, that's a plan view. You're looking down, and you see a red little mark. That's where we put the dampers there. And one at the right side, looking at elevation, which means looking from a side view of the buildings, and the location with dampers you can see. So it's not like everywhere, just a certain location you provide. In this case, what we try to do is this building twists a lot. So provide these dampers to reduce the so-called torsional effect. That's that thing we're doing there. It's really important thing is that really understand what is the weakness of that structural system and surgically apply the technology to surgically remove the deficiency. That's important because that makes the feasible, cost effective. That's a very, very important thing to do. Engineers, we want to make it perfect. We want to make everything's good from fixed from the top to the bottom or just throughout. But if you're doing that in a process, it's just not possible for private sector to be able to pay such a thing. So when we do things like that, it actually stop that any kind of a, this kind of a strengthening or something like this, then it's actually, we create a much more dangerous condition. So that's why it's very important to we engineers and architects and engineers to understand we need to really think about investment components of it, then that we can really create the market to do things like this. Because if doing things like this, actually, it's added values, to that value of the construction itself. There's a market value exist. That's the kind of, we have to look, it's that's a very important part of it. Now here, looking at little graphs here, that vertical axis shows the height of a building and the horizontal axis shows how much it's moving at. So you can see that actually movement of a structure at the very end, you cut back in half, just adding a few locations, these damping devices. And here's a little motions you can kind of see before and after picture. And it's really actually subtle movement difference, but you can kind of see it, which is moving more than others, So, but this little things like that makes a huge impact in the probability of a collapse. You don't make the 100% safe, like you can make the 100% earthquake-proof building, but you can significantly reduce the probability of a collapse by just doing something. So this is what can be look like. The structural engineering can be beautiful. I'm sure that many architects, in this room may agree. Okay, so what need to do for existing commercial buildings? I think we need to really think about not like performance-based, like let's say that, we like to say, engineers like to say, let's do life safety performance, or let's do collapse prevention performance. We can say anything we want. The problem is that if there's no money to be able to do that, nothing happens. Even places like California, there's actually a law passed. I'm talking about like 30 years ago, well, maybe 20 years, I don't know, something. It's a long time ago, to do seismic strengthening of a hospital to just at least meet the life safety performance per ASC 41. I think this ordinance was something like, I don't know, 2000 something, it's a while, long ago. Today, 2025, has not complied yet. Not every hospital hasn't done. And now deadlines push back 2030. And most likely going to push back again because hospitals can't afford doing things like that. So that's the whole point. Has to be cost effective. So it's not about performance-based engineering. Question of how much investment can be made, and that would be the basis of design should be. Because if you think about it this way, let's say that you got high-rise buildings. It may cost $10 million to do, let's say, the life safety performance criteria per AC 41 or whatever, right? Many different codes out there, guidelines. That may cost $10 million. But first, let's say only investor can afford to pay $2 million. That first 20% piece, that is really impact. That can really reduce the probability of collapse significantly. First 10, 20% of money is much more worthwhile than next 80%. So we like to spend all of them, but if there's money, what we're going to do? We're going to spend a little bit. So it's really coming down to the reduction of a probability of collapse. I think that's how we need to focus on that. Depends on what money is available. So something like this. I think we should have a limited seismic strength cost less than, say, 5% of market value or something like that, And I know the international funds, they are ready to provide liquidity to the market, directly to the commercial banks, to provide it very affordable liquidity, cash capital into the market to do this work. And if the government can provide certain property tax forgiveness, I know that here, Bangkok property tax for those high-rise buildings around 0.3%. Let's say if you can give a forgiveness for next 5 years, that's provide a cash flow to do things like this. It's the government's going to lose money? I don't think so, because that's going to create the construction activities. That itself to cause the actual income too. So yes, government need to be in a part of this, just no question. But it's definitely that as engineers and architects, we need to really understand what we're going to ask society to do. We can ask anything we want, but if you ask too much, nothing will happen. This always happens everywhere in the whole world. We just got to make sure that risk is reduced, not eliminated, because it's not affordable. I think that's a very, very important lesson we learn from all over the world. For the new construction, actually a little easier, by the way. We've been talking to a couple of developers here that, they are very, very serious. I think commercial sector is very serious about this risk, and capture long distance earthquake demand is a very, very important subject, which really need to be addressed in the building code and guidances. And with the cost-effective technology like using dampers, it does not add a huge amount of cost at all, to make it better. Doing that, investors can gain back confidence from public and market and the banking industry, and it will also affect the insurance also. That's about it. Yeah, this is something that we've been talking about for past 15 years now. And unfortunately, what we forecasted 15 years ago became real, and we lost many people, but maybe this tragic event will make this country and city safer and save lives down the road. It's definitely the lesson we learned to do this. Thank you very much. I lost the audio. I lost the noise though.
And this time he has many commitment also. So any questions, please? No question, I ask question. Dr. Kit, you mentioned last time that you would like to help improve the healthcare and hospital and schools. Have you done that since last time? And this time you propose also to help look into that facilities, apart from the commercial buildings.
Yeah, I'm sorry, I lost your audio for like 5 seconds.
Okay.
Could you repeat the question?
Okay. I remember in 2011 you mentioned about improving the schools and healthcare center in Thailand, in Bangkok. Probably you have not done that, but this time you propose again, and including also commercial buildings. So what you talk about is this time?
Yeah,
What's your plan?
Well, plan is last time was not so successful, right? If you think about it, you know. But plan is really I think I would just take the advantage of this public awareness of this risk, and just gotta push, And what's going to happen is this earthquake affect the Bangkok, and generally speaking, people are going to remember about 5 years. After that, people don't remember. That's how it works like that. So there's a really short time to really, push this agenda for safety. And yes, I think a commercial environment may be a little easier because there's a heightened needs in the market to do this, but also the schools and hospitals. Yeah, it's definitely it should be looked into that.
Any more question? And oh yes. Could you please, Professor Thirapan? Professor Thirapan.
I quite like the idea that there is going to be tax incentive. Could you please share your experience about this one in other country? That would be very great.
Yeah, I think so too. I think that's some of Japanese municipalities done that, and it's definitely to have a tax incentives, which makes a huge difference, right? And that's one of the best practices I've seen. It's not easy to implement it because of the just kind of have to change the whole registration aspect of that. The whole there's a policy components involved, so it may take some time, but this is definitely at the right time to do things like that. Just give you a motivation for the liquidity for building owners to do. I mean, people may think that they have a whole bunch of money sitting there to do anything, but it's not like that. It's money has to make it work. So it's definitely the having any kind of help like that, having the tax so-called forgiveness for a few years, and having an international agency like World Bank to set up their liquidity in the market, cost affordable liquidity. I think things like that would have a huge impact. How the private sector, not only private sector, but also the hospitals, and there are many large private-owned schools too. They can tap into things like that.
Okay. Thank you so much, Dr. Kit Miyamoto. I look forward to collaborate with you in the near future. I know that you will come to Bangkok next week, right?
Yeah, I'll be back next week. That's right.
All right. Let me know if you have any things to do, and if you require assistance, please let us know. Thank you very much for your contribution. Yes, your great contribution. The next speaker will be the last speaker for today. We'll talk about earthquake data analysis and decision support technologies. This will be presented by Ms. Victoria Lead, Asia Program Advisor, Pacific Disaster Center, PDC Global. May I invite Kun Victoria.
Good morning, everybody. Thank you for this opportunity to join this very interesting workshop and discussion. I've learned a lot today, so thank you to all the previous presenters. I'd like to just share my presentation. So some of you may be familiar with the Pacific Disaster Center, others maybe not. So I'll just share a quick overview of the organization and the work that we do. So we have a global mission. As mentioned, we are PDC Global. We've rebranded in recent years, reflecting our kind of global reach with the activities we undertake. We're really focused primarily on disaster risk reduction, helping to reduce losses and enhance resilience across the world. We're focusing on really using innovative technologies and applications. We're an applied science and research center under the University of Hawaii, and we're really looking to utilize the kind of latest technology and advancements in relation to disaster risk reduction to improve lives and protect lives and livelihoods. We're award-winning. The work we've done has been celebrated and recognized by the UN in 2022 with the award in the Sasakawa Award for the work we've done around disaster risk reduction and decision making. So we're very honored to receive this award. We've been in operation for more than 30 years. As I mentioned, we're applied Science and Research Center. We're managed by the University of Hawaii. Our headquarters are on Maui, but we do, as I mentioned, have a global reach. I'm based here in Bangkok. And we work with partners across the world, 75 different partner nations. We've been engaged with more than 300 successful projects. We work across all hazard types. And we have a disaster alert app. If some of you may be familiar with this app, you're welcome to download it. It's a free app providing you with the latest hazard information across the globe. So as I mentioned, global reach. We work with NGOs, non-government organizations across the world, as well as national disaster management agencies and regional disaster management agencies, and international and regional organizations such as the AHA Center. So you may be familiar with the ASEAN Humanitarian Assistance Center for Disaster Management. We have a very close working relationship with them since their creation. And continue to work both regionally and globally with many international partners. This is a list of just a few of our partners. Some of you may find your own logos here included, but you can really see we're a small team across the globe, but we work with many different partners and really very fortunate to work with a wide range of exceptional partners across the globe. So what we really look to do with the work at PDC is to bridge that gap between the scientific community and the decision makers. Today, you've heard from some very technically skilled individuals who are providing, excellent data supporting our understanding of hazards and their impacts. But what we really look to do at Pacific Disaster Center is to put that information into a usable format for decision makers. So people who maybe aren't seismologists, aren't experts in a particular hazard type, can easily absorb the information and understand what that may mean for their communities that they're charged with protecting, and what kind of decisions need to be made in order to support response and to protect lives. We saw some of this information earlier, lots of very detailed technical information, really important information, really necessary to understand exactly what's happened in regards to an event, whether it's an earthquake or a tsunami, hurricane. But sometimes that information can be quite difficult to digest if you're not kind of a specialist in that area. So what we look to do is bring that information into a very usable, kind of user-friendly tool that can be then used by decision makers to help them quickly and more easily make decisions based on quality information, the best information that's available. Here you can see some of the work, and I'm going to talk about this in more detail later, but some of the information products we're able to produce using that science and technology, that research that's being done by so many of our excellent partners around the world. So we really focus on an integrated approach to the way that we work. So we're using observation and collection systems, so whether that's tsunami buoys, satellite imagery, the seismic monitoring stations. We take this information and we're combining that with the advanced modeling. You saw earlier some of the fantastic shake map modeling that's done by USGS in relation to earthquakes, but we're able to integrate the modeling and the risk analysis. We also bring in the GIS and visualization systems, so particularly around satellite imagery, but using mapping tools to really make a visual, easily digestible information product. And then using computing and communication technologies. So we heard earlier about some of those tools, the testing of the cell broadcasting that will take place in May, leveraging those existing technologies and bringing all of those pieces together to support decision makers in their response and decision making. So we know there's a lot of data available, particularly when it comes to some certain hazard types. We get a lot of complex, interesting, useful information. But again, often it's not necessarily reaching the people who need it for decision making. And also it's often in not a very usable, easy to understand format. So what we do at PDC is take all of those different tools and all those different information sources, and then we're really starting to leverage AI a lot for our work, but using this information to undertake analysis for early warning, advanced analytics, and modeling, and bringing those together and serving them to the decision makers, making them available for the people on the ground, making decisions and needing to respond to events. So our flagship product is Disaster Aware, which is a web-based early warning and decision support tool, and it's utilizing all of those pieces I just spoke to support decision making and providing a tool that's a sort of in your hand or on your desk, depending on where you're using it, tool that can give you all of that information, again, in a kind of usable, easy to understand format. So this Disasterware tool, we have a number of different versions, but Disasterware is the overarching platform that we utilize. It has a smart alert early warning, so we're able to say when a hazard occurs or is expected to occur, if there's a forecast for an event, this is the area that we expect to be impacted, and so we can send out an alert to the users of the system and say, you've already told us you're interested in this area. We know that there's either been an event or there's likely to be an event in this area, so you can receive that near-time early warning. We also have an event brief, which is an analytics product that really helps you understand more about what the impacts of those hazards may be and what might need to be done in response to the event. We offer asset protection. That's a new function we've been working on recently, allowing you to indicate where you have assets that you want protected and receive alerts specifically related to those assets. And we also provide live cameras, so we're able to connect into CCTV cameras, to highway control cameras, to be able to monitor areas as needed. I mentioned earlier we have different hazard types. We have 28 different hazard types that we work with, so it's a multi-hazard system. And it really is the only system around the world that's providing a global early warning and impact analysis and assessments for flood, landslide, and wildfires. So we've been working very closely with NASA to develop this global alerting tool, and that is then integrated into the system. So working closely with the NASA teams, their model of models for flood modeling and landslide and wildfires, we're able to pull that information into the system. It gets plotted onto the map as a kind of usable kind of point on the map that people can easily understand, and then it pushes out an alert to users to say this event is expected to occur, and then also this is the information about what kind of impact we are expecting based on the information that's available. So a really powerful, very quick, automated tool that allows you to receive up-to-date hazard information in your hand. I mentioned earlier about those kind of analytic tools, and I'll show you later the tools, the products we created specifically for the Myanmar earthquake. But here you can see this event brief. So this is generated automatically for any hazard in the system, and it's using the information. So whether it's, in this case, an earthquake, it's using the shake map from USGS, and it's pulling in information about what's in that area that is impacted according to that shake map. And we'll, of course, we'll be focusing on the kind of most severely impacted area. But it's showing us here population exposed, so who's in the exposed area, and then also a breakdown by vulnerability. So it's not just saying total population, but maybe some of those particularly vulnerable groups that may need additional assistance. But you can also see it's showing us critical infrastructure that's within the impacted area as well. So not just showing you where the earthquake is or what the magnitude is, but helping you understand what really might be the impact and what might need to be done as a result. And you can see that final column in this product is the breakdown of key needs. So it's doing an analysis, again, based on the population and the expected impact to give you kind of rough numbers, just when you're getting started, of course, needs to be verified on the ground, but giving you an initial understanding of what kind of response is needed, what kind of needs there may be based on the available information. I mentioned this Smart Alert tool, so you can actually set up your own Smart Alert settings. So if you have access to the system, and anybody working in disaster management in this room is welcome to apply for an account. If you don't have one already, it's free to use. And this allows you to really customize the kind of alert. So you could say, I'm only interested in Thailand. So you create a kind of geographical filter just for Thailand. And you say, I saw earlier from NDWC, the kind of key hazards that Thailand is focusing on. You can say, I'm only interested in these hazard types, and then the alerts will be very much targeted based on those specific needs that you have as a user. So completely customizable for each individual user as well. I mentioned that this is the disaster-aware platform, but we do have a number of different tools that come from this platform. We have a version that we run at PDC called Disaster Aware Pro, and that's the global version for disaster managers that we manage and maintain. But we've done a lot of work over the last 20 years on the customization of this system for specific contexts. So we understand that every country, every government has their own needs and requirements, their own legislation about what they have to, which information they have to use for their decision making. And so we've worked closely with individual governments. So in Indonesia, Indonesia and the Philippines, they have custom versions of the system that they're using operationally. So InAware and PhilAware are being used operationally. And then at the AHA Center, as I mentioned, they have a custom version themselves as well, that is used not just by the AHA Center, but also by the national disaster management organizations of Laos and Myanmar. So we were able to work directly with those governments to help them build capacity to utilize the regional system as well. We've also done a lot of work globally in the Balkans region and also with the International Atomic Energy Agency to bring them custom tools based on disaster aware to support their specific needs in relation to disaster risk reduction. This is just an example. I mentioned the Philippines. You can see here, this is their Emergency Operations Center, the top picture here. This is the system. It's running 24/7 in their Emergency Operations Center. They use it for monitoring and responding to events. You can see here they're monitoring a storm event. And then the picture at the bottom is actually a kind of customization of the map. So you can actually go in and annotate the map as needed. And they use this to plot after an earthquake in the southern region of the Philippines. They were able to plot the areas that were impacted and what kind of impact was observed in each of the different areas around the earthquake epicenter. So you can see here kind of operational use of the system for a variety of different uses. This is just showing two, but we've been very kind of interested to see the creative ways that the system gets used by different governments and different users for their specific needs as well. Here's another example as well, just plotting some of the impacts, again, of that same earthquake that occurred. So a little bit just about the March 28th earthquake and the way the system was used. Before we even go into the other slides, you can see here, this is the Emergency Operations Center at the AHA Center. Again, they have this custom version of disasterware. Their version is called DMRS, the Disaster Monitoring and Response System. And this system here, you can see up on, again, 24/7 available up on their screens in their Emergency Operations Center, used to monitor and respond to events. But the operations team also have their smart alert notifications customized. So even when they're not staring at the screen, they can receive an alert on their phones and know that they can go to the system and use it to kind of review any hazard events as they occur. So this is just a photo of them using the system during that. They've been obviously supporting the response in Myanmar, and this is the system being used to support that. So a few key pieces. So when the earthquake occurred, this is the smart alert that you receive. So I mentioned that notification, near real-time alerting. As soon as the system receives the earthquake notification from, at the moment, USGS, but we're working to bring in a regional source as well from IAEC. And you can see here, this is the actual alert that's received. So it's just a very straightforward, clear outline of the event. So it would vary depending on the event, but this is obviously the March 28th earthquake. So telling us there was an earthquake and showing us some short information about the hazard and what kind of estimated impact there is for this hazard. You can see there's also a link here at the bottom to Disasterware Pro. If you click on that link, you'll be taken to the login. You can log into the system and it will take you straight to the hazard information about this specific hazard. So this is just giving you that notification, and then you can go into the system to really dig around and understand more about the specific event. When you go into the system, this is what you would see. So as soon as you click on that link and go in, this is the user interface of the system here. And you can see what we've done. We have the hazard itself showing here, and it's telling us a little bit of information about the hazard. And then we've overlaid, and this is all done automatically. So as soon as the hazard comes in, it also pulls in that USGS shake map that you saw earlier as well from the previous speaker. And it's allowing us to understand, again, a little bit more information about the hazard, what kind of impact we're expecting based on that that shaking, the shake model here. And then, as well as being able to see that information, you can also overlay lots of other data like base map data in relation to critical infrastructure, population. You can bring in all of these data sets as well. So we're working with lots of different data sources. I think DisasterWare has nearly 10,000 data layers in now, so many different useful data sets that can be overlaid on that user interface to see more information and understand the situation. But we also work closely with the World Food Programme and UN OCHA to create what we call the joint analysis of disaster exposure. So this is a specific product that we develop for large-scale events, and we work closely with WFP and OCHA, who provide us with some of the field data that we can then use to analyze the impacts and produce this product that can be used to support decision making. So we're able to run the analysis based on that information that we receive, the field data we get from WFP and OCHA, along with the shake map that we have from USGS to provide this product. And you can see this really, there's a lot of information here on quite a small space, but you can see the kind of impacted population, again, breakdown by some of the vulnerable groups, but also by those living in the worst impacted area. So it's using that shape map to understand, the most severely impacted. But then you can see it's also showing key needs and critical infrastructure here. And the bottom table is a breakdown by specific areas as well. So if people are going in to provide support to a specific area, you can see here it says Mandalay, we have the different areas within Myanmar, then you can look specifically at that area and what we expect is needed. The nice thing about these kind of products as well is that we would run similar ones for each impacted country as needed. So if an earthquake, for example, goes over into another area, another country, and it's significant impact, then we would be able to develop a similar product as well. So this isn't an automated product, but we do have automated products as well. So as soon as the hazard comes into the system, all of that analysis is run automatically and pushing out the products that can be used for decision making. This product we actually continue, although we don't have an active project with the Indonesian Disaster Management Agency, BNPB, at the moment. We do maintain a very close working relationship with them, and they indicated that they used this product to assess the required assistance from their side. So they were providing support to Myanmar, sending support, and so they were able to utilize their version of the system, the InnoWare system, which would also have this product. This product was integrated into their system. They're able to access this product through their system and use that to make their decisions about what kind of support to provide. And as I mentioned, similarly with the AHA Center, they use this product and you're able to kind of glean a lot of information that can be used to support the response. So here's just a little bit more information about how the AHA Center used their version of the system. So again, just pictures of the system in action whilst they're conducting briefings and coordinating their response. And that middle picture is their situational updates, which some of you in the room may receive already. So this is one of their situation update products, and you can see that the system itself, that information from our system, from the DMRS system, is the main graphic that's used to kind of tell the story of what's needed, what kind of impacts are expected, and to again help with the decision-making process as well. That's all I have. Welcome any questions. Thank you very much.
Thank you so much. Very informative and very interesting. Would like to ask the floor if you would like to have any questions and comments, please. Not yet. I can help you ask first. The AHA Center is in Jakarta. It's for ASEAN. And I can understand that this center also linked to all the ASEAN government. and collaboration between PDC and AHA Center is very, very fruitful. I would like to know that during the Mandalay earthquake, how, for example, government of affected country like Myanmar and Thailand has utilized these alert and information for their benefit. How can we check on that? Maybe Thailand can answer first, that how you look into AHA website, or you may have Thailand own alert, but this ASEAN alert is very useful. And as I like to recall that PDC have helped Thailand during my time on disaster aware, very useful information system and decision support. Can speaker respond or Thailand respond, please?
Yeah, thank you. In terms of, as I mentioned, we previously worked with the Myanmar government. We were working with the Department of Disaster Management and the Department of Hydromet as well. And that was a very fruitful project. They were actively adding hazards to the DMRS system. So they didn't have a custom version of the system themselves, but they were able to leverage the DMRS system from the AHA Center. And previously, before the coup, we were able to kind of remain in communication with Myanmar and understand their use of the system. Since the coup, we've had very limited communications with them. So it's quite difficult for us to really check on the use of the system. It remains open for them to be able to use the system, but we haven't been able to confirm whether they're able to utilize our products for the response. I know, as I showed you, the World Food Programme, OCHA are able to utilize these products for their response and support to the country, but it's not clear to us to what extent the government themselves have been able to continue to leverage the system.
Thank you very much. I can understand that having redundancy is good in emergency time. Like in case of tsunami, for example, if you have not only one warning system, you have backup system, you have redundancy that can confirm, and you can utilize that various source of information. For example, now you have AHA Center, we have PDC, we have each country system. Do you think that these are benefit more than competing?
Absolutely, yes. The redundancy, I think, is really important. We've seen that be a very useful tool in Indonesia, their version of disasterware, InAware. We've been able to bring in their national earthquake information. So we have the global version, we're using USGS as the earthquake information. But they, as we talked about customization of the system, we customized the system to bring in their earthquake information from BMKG, their national seismic monitoring center. And so now they're able to see both of those. So they're able to validate their data against it. So of course, we know there's a requirement to use national data for decision making, and legally there's a requirement. But of course, it's very helpful to have that additional information that they can utilize as part of the decision making and to verify data as they go along. Yes, yeah. So no, we never see it as a competition. It's a useful complement, I think. You need a number of tools. There's no one tool that will do everything, but having a range of tools provides you with a kind of broader understanding.
For example, when director mentioned about the cell broadcast system, that there's still a limitation for certain level of communication system. Do you think how can we fill up the gap utilizing PDC technology? Is there any way?
Yeah, so the notification service that we have at the moment is restricted to the disaster management community, the decision makers, rather than the public alerting. We've kind of done a proof of concept that we can do the public alerting if that was desirable, but it's not something we have expanded into at this point. But I do see, and I was talking to our colleague from NDWC earlier, particularly around deciding on the impact areas, leveraging different kind of models for impact areas of where that, the cell broadcast may go. Also understanding maybe who's in that cell broadcast area at that time, if there was a way to receive information back to say, okay, we sent out this alert, it was received by this many cell phones, that would give you a better understanding of who's in the area and maybe what kind of impact there is as a result. So there's definitely room for discussion and the enhancements. As I mentioned, we're not looking at public alerting at this moment, but there's definitely opportunities to leverage some of that data, the analysis pieces, to support the kind of robustness of those alerts as they go out to the public.
Okay, thank you very much. Is there any more comments and questions, please? This can be in Thai also. Advisor Supawat can help translate. Okay, so if there is no any question, I'd like to thanks so much to Ms. Victoria Reed from PDC Global, kindly contribute significantly to our workshop. Thank you very much. Thank you. We are on the right time. Now we come to the final session on reporting, wrap up, concluding commitment to future collaboration. I don't know whether the Vice President would like to make a concluding remark or you would like me to do it. You want me to do it shortly? Okay, thank you. First, I'd like to mention that, again, that all the presentation in PDF will be placed, maybe we'll communicate with ASA whether we should place it on the website of ASA, the PDF presentation, and also the team's website. We will, I would like to conclude shortly, very short, about what we have participated this morning. The President of ASA and the NDWC Executive Director have addressed and inform us on important workshop objective and welcome participants to attend this workshop. The President of teams mentioned that there are still gaps of communication that need to be improved, and this workshop may be the right platform that we collect some of the information and suggestion, and we put them in the final minutes. The final minute will be disseminated on the website upon approval by all the speakers. Now come to the speaker of the session, Professor Thirapan have mentioned about continue to research on improving seismic design, and that will be useful for scientific communities. The USGS, Dr. Mooney, commit to work with Thailand and relevant agency on capacity building for earthquake forecasting. The National Disaster Warning Center committed to improve their communication system early warning, and in order to effectively reach the target last mile. And they are developed the cell broadcast warning system, which will be useful for people in the near future. He commit also to work with teams for any important or useful event to be organized in Thailand. Also, teams plan to do a training and conference in different countries. So hopefully NDWC will nominate someone to join. Okay, thank you. Miyamoto International commit to work with private sector on investment on not only performance-based but also investment-based. And right away, Miyamoto International will come next week to work with the private industry, which is very useful. The Pacific Disaster Center has mentioned about making information meaningful, data for life. And PDC has invest on knowledge-based information and work with so many partners and stakeholders. And PDC will work with not only Thailand but other countries to look into how to provide information for decision makers in terms of disaster. So these are the wrap up for today. And in my final minute of the meeting, I will disseminate to all the speakers for them to check and add on, and before placing them on the website of ASA and teams. Now, the concluding remark will be very short. I just want to mention about my own experience when I first joined disaster issues in 2005. I'm in fact background in fisheries. You may wonder why I'm dealing with disaster. Yeah. Anyway, I'm working with community, so I'm familiar with how to make community understand the issue. If you recall the tsunami in 2004, prior to that, the tsunami warning system has been established 50 years before that. So people know tsunami, but many people do not know. And in Thailand, I could mention his name, Dr. Smith Thammasarot. Somebody may know him. He is the Director General of Thai Meteorological Department. He has warned Thailand about possibility of tsunami, and it happened. But because we do not know about tsunami so much, they did not prepare. And that's why many people die during that period of time. So we learn from experience, and we develop now 20 years tsunami warning system. We have 3 tsunami watch provider in Australia, in India, and Indonesia. So we hope that when the next tsunami comes, we are safe. And each member country of Indian Rim, 17 countries, we have developed their national warning system, be able to protect life and property of people of Thailand and people from abroad who visited their countries. Now, as you know from the President, 2011, we organized the conference on the effect of distant large earthquake on Bangkok and major cities. We discussed 2 days, and we're providing with commitments, about 8 commitments. Only 2 were implemented. Anyway, we don't go back what we have not done. But today, it happened. So now we have to do something that we commit to do, even 15 years ago and today, that we commit to do. And I hope that we should not avoid doing that, because it's very important to act at the moment in order that we can proceed. We can even to see whether we can propose this to the government of Thailand, if some of the commitment can be operated. You know, my last but not least, I would like to extend my sincere appreciation to the Association of Siam Architects under Royal Patronage, ASA, and relevant partners, speakers, and participants who are attending this in person, as well as people who participate in YouTube. You know how many people attend YouTube? I won't tell you. Okay. So on behalf of the president of teams, I would like to extend sincere appreciation to the ASA and partners, as well as participants, invited speaker, and look forward to collaborate with you in the next event. And hopefully we can have more time to prepare. This time is too short, so next time will be in more detail and on a specific issue, and will benefit. And we will inform you of what we are going to organize, and we'll invite you to attend if you are interested in. Thank you so much for today's workshop, and look forward to see you in the near future. Please note that this afternoon session will be carried out from 1 o'clock, but it is in Thai. So if you understand also Thai, you can attend. I would like to invite foreigner to attend also. But there is no translation this afternoon. No translation. Yeah. So, but there will be a kind of a presentation. Yes. So if you are interested in, you can attend in this room also, in this room. Thank you very much, and have a good day. Thank you.